All right, today we are pulling back the curtain on the invisible world of electricity. We're going to uncover the secret rules that tell us exactly how electrical conductors behave. We'll be looking at what happens when you take a piece of metal, something like a sphere, and stick it in a static electric field. So here's what we're going to cover in this explainer. First up, we'll nail down what a conductor actually is. Then we're going to peek inside to see what's happening when an electric field shows up. After that, we'll check out what's going on at the surface or on the edge. And all of this is going to lead us to a conductor's most amazing trick before we wrap it all up with a quick review. But before we dive into the heavy physics, let's start with a question you've probably thought about. You've always been told that if you're in a thunderstorm, one of the safest places you can be is inside a car. But why is that? A lot of people think it's the rubber tires, right? Well, spoiler alert, it's not. The real answer has everything to do with the rules we're about to break down. Okay, first things first. To get a handle on these rules, we've got to know who the main players are. So what really makes something a conductor? And what makes it so different from, say, a piece of wood or plastic? The single most important feature is right here: mobile charge carriers. You see, in metals, the outermost electrons in each atom are, well, they're not very attached. They can pop off really easily and are then totally free to just wander around the entire piece of metal. It's almost like they're a community of electrons that don't belong to any one single atom. Yeah, a really great way to picture this is to think of all those free electrons as a sea or even a gas that's just filling up the entire metal. They're zipping around all the time, and this is the crucial part. They can be pushed around by electric forces. This incredible mobility is the key to, well, everything else we're going to talk about. And that right there is the fundamental difference. In a conductor, like copper, you've got this massive sea of electrons just ready and waiting to flow. But in an insulator, like rubber or glass, the electrons are locked down tight. They are bound to their home atoms, and they simply cannot get up and move around. So, we've got it. A conductor is full of free-roaming electrons. What happens when we put that conductor into an electric field? Let's uncover the first and most important secret rule, the one that controls what happens deep inside the material. This is the big one. This is the master rule that everything else comes from. In a static situation, meaning things have settled down, the electric field inside a conductor is always zero. I don't mean it's weak or small. I mean it's perfectly, completely zero. But why? How is that possible? Well, it's all because of that amazing sea of electrons. Picture this. An external electric field comes along and tries to push its way through the conductor. Instantly, that field starts pushing on all those free electrons, making them drift. They start to pile up on one side of the conductor, which leaves the other side with a net positive charge. Now get this. This separation of charges creates its own electric field inside the metal, pointing in the exact opposite direction of the external one. The electrons keep moving and piling up until their internal field gets just strong enough to perfectly cancel the external one. So the net result inside, zero field. It's an incredible self-correcting system. And this zero field rule has a couple of really amazing consequences. First, any extra charge you try to put on a conductor gets immediately pushed to the outer surface. It just can't hang out inside, because if it did, it would create an electric field, and we just figured out the conductor won't allow that. Second, the electric potential, you can think of it as voltage, is the same everywhere, inside and on the surface. It's like a perfectly level body of water. Since there's no slope, no field, it takes zero work to move a charge from one spot to another. Okay, so we've established that the inside is quiet, zero field, and all the extra charge has been kicked out to the surface. This means all the interesting stuff is happening right on the edge. So that brings us to our next set of rules. And this leads us to rule number 4. The electric field right at the surface has to be pointing straight out, perpendicular to the surface at every single point. Why? Well, just think about it. Imagine for a second the field was slanted, even a little bit. A slanted field would have a sideways component, right? And that would push the free charges along the surface, creating a current. But we're talking about electrostatics, where everything is settled and not moving. The only way for those charges to be at rest is if there's no sideways push at all. That means the field has to be pointing straight out. And this diagram shows it beautifully. Just look at those electric field lines, the ones labeled with an E. See how every single one of them hits the conductor's surface at a perfect 90-degree angle. None of them are coming in slanted. It's a hard and fast rule. So, we know the direction of the field, but what about its strength? How strong is it? To figure that out, physicists use a really clever little thought experiment. They imagine a tiny little cylinder, what they call a Gaussian pillbox, that's poking just halfway to the surface of the conductor. By analyzing the charge inside that tiny imaginary box, they can come up with a surprisingly simple formula for the field's strength. And this is it. This is the result of that thought experiment. Now, the formula might look a little intense at first glance, but it's actually super straightforward and incredibly powerful. It tells us the exact strengths of the electric field right at the surface. Let's just quickly break down what these symbols mean. So E is the electric field strength we're looking for. That Greek letter sigma just stands for surface charge density, which is a fancy way of saying how crowded the charges are on the surface. And epsilon naught, that's just a fundamental number of the universe, a constant. So the relationship is actually dead simple. The more charge you pack into an area on the surface, the stronger the electric field is right at that spot. That's it. Okay, now we get to the grand finale, the most dramatic and useful application of all these rules combined. It's a phenomenon that we use all the time in the real world. And here it is, our fifth and final rule, which leads to something called electrostatic shielding. If you have a conductor that's hollow on the inside, like a metal box or a sphere, the electric field inside that empty space is always zero. It doesn't matter what's going on outside, you could have a massive electric field raging, but inside that cavity, it's a perfectly protected, field-free zone. This diagram shows us exactly why. Just like we saw before, the free charges on the outside of the conductor rearrange themselves to cancel any external field within the metal itself. But the amazing result of that is that the empty space inside the cavity is also left with a zero field. The conductor forms a perfect shield, totally isolating its interior from any electrical drama happening on the outside. And this brings us right back to that question we started with. Your car's metal body is a conductor, a hollow shell. When lightning strikes it, that enormous amount of charge flows over the outer surface, while the electric field inside the car stays at zero. You are safe inside what is basically a Faraday cage. This exact same principle is used everywhere to shield sensitive electronics, like in a hospital or in your computer, from stray electrical noise. Wow, okay, we have covered a lot of ground. So let's just take a moment to bring it all home and do a quick review of the complete rulebook for conductors in electrostatics. Here it is, all in one neat package. Inside, the field is zero because those free electrons are incredible and move to cancel any external field. That, in turn, pushes any extra charge to the surface and makes the voltage the same everywhere. Then, at the surface, the field has to be perpendicular, otherwise charges would be moving. And finally, in a cavity, the field is also zero, creating that perfect electrostatic shield. And as our source material puts it so simply, the field inside the cavity is always zero. This is known as electrostatic shielding. It's an absolute, powerful, and incredibly useful property of conductors. So let's end with this thought. These rules aren't just something you find in a physics textbook. They're actively working all around you. This shielding principle is at work in the braided metal of the coaxial cable that brings you your internet, and it's in that metal mesh on your microwave door that keeps the microwaves safely inside. Now that you know what to look for, where else can you spot these invisible force fields at work? Thanks for joining me.